Hello everyone and welcome to MV Tutors. I'm Tsulu and I'll be looking at vertical projectile with you, scenario number 4. Okay, so far we've covered scenario 1 where a ball was just dropped or a projectile was dropped. Then we had scenario number 2 where a projectile was thrown. Scenario number 3 where a projectile was bouncing. And now scenario number 4 where we have a projectile dropped out of a constantly moving vehicle, if I could say. So looking at a hot air balloon that is moving at a constant velocity, and we have a ball that is dropped, or rather a projectile that is dropped from the hot air balloon. Okay, so I haven't done an example like this. I went and browsed like all the past papers trying to see which one has it. So I found one in 2017, the February/March SUP, as well as the 2011 November exam. That's how far back I went to get examples, because we saw this in the 2021 November exam. So yeah. My experience though with projectile motion, especially if something is thrown or dropped from a moving vehicle, let me just say vehicle, it's in first year physics, but then we do projectile motion in 2D. So I've seen like an airplane dropping some boxes or whatever, but for matric, I guess now with projectile motion, vertical projectile motion in one dimension, if you're gonna have something that's moving and a projectile thrown or dropped outside of it, it's going to be something that's light, like a hot air balloon. Okay, so let's see what kind of questions we have here. But before we begin, please don't forget to like our videos and also subscribe to our channel. Please also just click on the notification bell if you would like to get notifications whenever we post a video. Okay, and if you would like a private session, please do visit our website www.mvtutors.co.za, and we'll be happy to assist you. You can book there, especially for a free consultation. Okay. So question 3, November 2011. It says a hot air balloon is moving vertically upwards at a constant speed. A camera is accidentally dropped from the balloon at a height of 92.4 meters. Oh, it's gonna break, right? As shown in the diagram below. The camera strikes the ground after 6 seconds. Okay, so we're gonna ignore the effects of friction, because we know in real life there's also air friction working against this dropped projectile, which is a camera in this case. So now 3.1, it says, at the instant the camera is dropped, it moves upwards. Give a reason for this observation. Okay, so because, before I even answer, think about a scenario where you are in a car, okay, and you're not wearing a seatbelt, and then let's say the car is moving at 80 kilometers an hour and then it crashes. So are you going to stop immediately, or will you still move at the speed that the car was moving in? Well, you will. That's why some other people then would be thrust out of the car, maybe through the window, and it's a hectic accident there. So the seatbelt helps to keep you still, but honestly, if you're moving with a car at a speed of 80 kilometers an hour and it gets into an accident, like instant collision, it stops right there and then, you will tend to move because of inertia. You will still tend to move at that very same speed before you come to a standstill. Okay, so in this case here, this camera was going with the hot air balloon at a speed that we don't know, but it's a constant speed. Okay, and so before it is dropped, okay, so you won't get a scenario where there's a train moving there. What am I doing? Okay, so let's say we have the hot air balloon there. It won't be a case where the projectile is there and it's just dropped. Okay, the motion, actually, it will move up first with the hot air balloon at the speed of the hot air balloon, and then only then will it go down. All right, so when it says at the instant that the camera is dropped, it moves upwards. Okay, give a reason for this observation. Well, that is because the initial velocity of the camera is actually equal to the constant velocity or the constant speed. Let me just put it there. Constant speed, meaning that it's actually not accelerating. Constant speed so it moves at the constant speed. So the speed of the camera, the initial velocity of the camera, is equal to the constant speed of the hot air balloon. Okay, that's 3,1. And now 3,2. Calculate the initial speed at which the balloon is rising when the camera is dropped. Okay, so this hot air balloon is not moving, or it's not in free fall. Okay, it is the camera that is in free fall. So if we want to calculate the initial speed for the hot air balloon, the only equation that would be applicable for the hot air balloon, since it is not in free fall, it would actually be this one here. Okay, where you have the initial velocity plus the final velocity over 2 times delta t. And because it's constant, the initial and the final, you don't need to get the average. You're just going to get v times delta t. Okay, that is the only equation that is applicable for this hot air balloon, because it is not in free fall. Okay, it is not accelerating. Okay, so now if we want to get the speed of this balloon, we would have to know, the time at which it was 92,4 meters. Okay, so we don't have that. All right, so instead of now calculating directly for the balloon, because of 3.1, we know that the initial speed of the camera is actually equal to the speed of the hot air balloon. All right, so we're going to instead calculate the initial speed of the camera. So again, let's have a look at the equations of motion. I have the height above ground. Okay, I also wanted to illustrate that since the camera will have this kind of motion, this distance here, okay, because it moves first up and then down again, it was quite negligible. Okay, so when you have your 92,4, I think, meters, this distance over here really is negligible. We're not going to take it into account. We're just going to stick to the 92,4. Okay, but now let's just answer the question. Ooh, my handwriting looks terrible today. But we are going to use where we have, because we know that our delta y is 92,4 meters. Wait, first we need to decide, are we taking up as positive or down as positive? I like taking down as positive, so let me try taking up as positive this time. Okay, so this is positive. So if then my 92,4 will be negative in this case, my g will be negative 9,8. What do I have as well? I'm looking for the initial velocity, and I know that the time it takes for it to reach the ground, we have 6 seconds. Okay, so we can use this equation where it says delta y is equal to initial velocity times delta t plus half a delta t squared. Okay, so what is our, because we're taking up as positive, and this ball is going to go down negative 92,4 meters. Let's just go down and make sure that we are writing the correct values there. 92,4 meters. Initial velocity is what we're looking for. The time it took is 6 seconds. Okay, and then we're going to have negative a half. Okay, because Our acceleration is going to be 9,8. So here we can use the equations of motion because the camera is a projectile and it is in free fall. And then time 6 squared. Okay, so I'm going to have 6 times VI, and then I'm just going to take this whole term to the other side. So I have negative 92,4 plus 0,5 times 9,8 times 36. Okay, so I have 84. All right, and then so the initial velocity of my projectile, the camera, oh, I didn't finish calculating. Okay, so 84 divided by 6 would be 14. Okay, so I have 14 meters per second. So this is the initial velocity of the camera, okay, the projectile. So we know that this would be the same as the speed of the air balloon. I want to say speed balloon. Speed of hot air balloon. Okay, and yeah, so that is the speed with which it is rising when the camera is dropped. Okay, now we can get to 3.3. It says draw a sketch graph of velocity versus time for the entire motion of the camera. Okay, so we're taking up as positive, right? So this this camera, I'm so used to balls. It went up and then it went down. Okay, so fine. This was the initial velocity, 14 meters per second, and then it reached 0, okay, before it went down, and then it got to some maximum velocity. Okay, we could always work it out. Out of interest, let us just do it since this question is going by quite quickly. So if I want to get my final velocity, I would say my final velocity is equal to my initial velocity. My initial velocity is going up, so this will be a negative 14. Okay, and then my gravity is going down, so it will be negative. I'm using this equation, sorry, initial velocity plus a delta t. Okay, so initial velocity is negative 14, and then my acceleration, because I chose up as positive, is going to be 9,8, and then the time it took for the whole thing was 6. So if I were to calculate this, I would get my final velocity should be negative because it's going down and I chose up as positive. So let's not be scared by the negative numbers. I was already thinking, what is going on? So 9,8 times 6. Something's not right here. Up is positive, my goodness. So yes, my initial velocity is going up, so it is positive 14. Right. So at the end, my final velocity is negative 44,8 meters per second. They didn't ask for this. Like I said, this is just for interest's sake, seeing that we have a little bit of time. Why not? Okay, so we're going to sketch a graph. Okay, so here we are at negative 44,8 meters per second. And, okay, so here we also have 14 meters per second. So this time here it was 0. Okay, and that time there it is 6 seconds. Okay, so let's just say 0 seconds, and that is 6 seconds. What is that time there when it got to the peak? Alright, so what I can do, I can still use the equation. My final velocity is equal to initial velocity plus my acceleration delta t. So my final velocity, I know it's 0 at the peak. My initial velocity is 14. I know that gravity is negative 9,8, and I'm looking for the time. So my time will be negative 14 all over negative 9,8. We can't be getting a negative time, hey? Oh, wrong thing. So we are going to get negative 14 divided by negative 9,8, and that is 1,43 seconds. So 1,43 seconds. So it took 1,43 seconds there to get up, and then for it to reach there, it's going to be twice that, so that's going to be 2,86 seconds. Okay, so we can plot, and the only thing they really wanted to see was the initial velocity and the time at which it strikes the ground. Okay, so our graph, ladies and gentlemen, I normally say guys, the way I say guys so much, my son calls us guys. He comes and he's like, guys, and we're like, what? We're not guys, we're your parents. Like, chill. Okay, so we have our velocity there on the dependent axis, the y-axis, that's velocity in meters per second, and then we have time in seconds. Okay, so our projectile, it started there at 14, that was the initial velocity, and then it got to 0 and then past 14, and then it reached the amount that it reached. I forgot that value. 44, negative 44. No, what am I doing now? Okay, so it's going that direction. All right, so we have 14 meters per second. Then it got to 0. It got to 0 meters per second at 1,43 seconds. Let's just say 1,4 seconds. And then it reached, let's just say this is negative 14. Okay, it reached negative 14 at, okay, so this is more precise, at twice that time. So it is 2,8. I'll just stick to 2,8. Let me see, what was it there? 2,86. Okay, 1,43, 2,86 seconds, and then it reached its maximum velocity when it struck the ground, which is negative 44,8. Okay, and the time that it reached there was 6 seconds, and that's all they wanted to see. They wanted to see the initial velocity as well as the time it took to reach the ground, which is 6 seconds. Okay, now the last question, 3.4. It says, if a jogger 10 meters away from point P, as shown in the above diagram, and running at a constant speed of 2 meters per second, so this person is not accelerating, if they see the camera at the same instant it is, no. So if a jogger sees the camera at the same instant it starts falling from the balloon, will he be able to catch the camera before it strikes the ground? Okay, so considering my equations of motion, I want to calculate the time it takes for him to get to point P. I know that the camera will strike the ground at 6 seconds, but I just want to find out how long will it take him. Then I'm going to compare the two answers, and then we're going to conclude. Okay, so we know his initial velocity and his final velocity are the same. Okay, so I'm not going to use the first equation or the second. I actually want to use the last one. Okay, the delta x. Okay, where we have the initial velocity plus the final velocity over 2. That's pretty much the average. Okay, and we have delta t. So that's basically saying velocity times delta t, because the velocity is constant. Okay, he's running at what, 2 meters per second? I actually forgot. Yes, 2 meters per second, and he's 10 meters away. So that would be 10, and his speed is 2. So let's calculate his time. Well, it will take him 5. Okay, both my 5 and the seconds look the same. Let me just rather do this. Okay, it will take him 5 seconds to reach point P. So, will he be able to catch the camera before it strikes the ground? Yes, he will be able to. And it says use a calculation to show how you arrived to the answer. We did exactly that. How many marks was it? They were quite generous back in the day. Okay, guys, so basically this is projectile motion scenario number 4. I'll see if I have enough time. Maybe we'll look at another example. I'll see. But if not, this is goodbye from me. Please don't forget to like our videos and subscribe to our channel. Also click on the notification button. And if you want a private lesson, please go to our website www.mvtutors.co.za.